We're getting to the end of this explosion series. We started with Taylor and Trinity, with the interplay of energy and density, able to rationalize the dynamics of explosions from tiny to astronomical, but not the whole course of the explosion. By studying the onset of explosions, we saw that the ejected mass initially plays an important role. And by wondering about the ultimate fate of explosions, we've seen that the ambient stress was indispensable. The goal now is to summarize the effects of this set of four mechanical quantities. You can write it in the order you like. The kinematic consequences of the interplay of these four quantities is given only by their dimensions. We call this set the explosion domain. First, let's recap the regimes of the domain that we have seen so far. We started with Trinity. We know this explosion quite well by now. No need to show all the pictures behind these data points, which follow a power law, Taylor's regime, the sole consequence of the interplay of energy and density. This 2/5 trend was confirmed by adding the full set of data from Mach's 1946 report, declassified in 1981. We can just merge the datasets. By considering short timescales, we realized that a steeper initial regime was necessary to avoid the divergence of the explosion front speed. In the last episode, we saw that this regime could often be understood as having a constant speed coming from the ratio of energy and ejected mass m. This is the energy mass regime, a simple consequence of dimensional analysis. The time resolution for the Trinity test did not allow much data to be collected there, but we saw that this regime has been captured in other explosions, large and small. For these two regimes, energy is the driving force. First resisted by the ejected mass, then by the density of the ambient medium. The switch in the resisting factor occurs when the swept-up mass becomes greater than the ejected mass, that is, when the radius is the cubic root of the ratio of mass and density, which is the mass-density regime. In episode 4, we looked the other way, toward longer timescales, beyond the range studied by Taylor. We figured the explosion had to stop at some point, and we saw that considering the atmospheric pressure provides a final blast radius, a balance between energy and stress. This length scale was roughly indicated by the maximum extent of the dust cloud on the ground. Whereas this final blast radius is around 1 kilometer, the final radius of the fireball is around 200 meters. A tenth of a second after detonation, the front of the explosion has separated into multiple components, with the fireball in orange and the shock front outlined in red, becoming increasingly transparent and moving ahead. The optical team at Trinity, led by Mach, tracked the trajectory of this shock front, which starts to move upward, away from Taylor's regime. And other teams continued the chase by using pressure measurements. Well, we're starting to have a pretty detailed record of the explosion. We even know too much for our purpose today. For now, we will forget about the fireball once it detaches from the shock, because we already have a lot to talk about. We saw in episode 4 that the shock front is moving away from Taylor's regime, because it is moving toward the sound propagation regime, that is, the regime associated with the stress-density pair. This regime at constant speed only depends on the material property of the ambient medium, its stress or modulus or pressure, and its density. At the intersection, the energy, the stress, and the density combine to produce a spatial space-time point, an event, which can be used as the origin of the Hopkinson-Krenz system of units. Here we've selected the speed of the stress-density regime such that it intersects where Taylor's regime already intersects the final radius. But this would imply a speed of sound around 230 meters per second, whereas the speed of sound is really around 340 meters per second. The three regimes do not intersect nicely anymore. Our very rough measurements of the final radius from the dust cloud is to be blamed. We'll see in episode 8 how to measure this radius more rigorously from pressure measurements, but right now we'll just drop these uncertain data points and lower the value of the final radius so that the intersection is recovered. The price we pay for being able to describe the explosion from microseconds to minutes is that the regimes that we can predict from the mechanical quantities are only approximate. Still, dimensional analysis is pretty efficient, given the minimal amount of math it requires. Once we know the pair of mechanical quantities involved, we can get the associated scaling for the size over time. In the case of Taylor's regime, we can symbolize it in this way. The order of the terms in the pair of mechanical quantities does not matter. Once a pair is chosen, the impaling and impeding factors are assigned automatically by the dimensions. If we start from this more general equation, the fact that energy and density are mechanical quantities carrying a dimension of mass implies that gamma equals minus beta, and the interplay of the space-time dimensions of energy and density imply that alpha be 2/5 and beta be 1/5. This is why we say that a pair of mechanical quantities implies the scaling, which we write like this to highlight the impaling factor in the numerator and the impeding factor in the denominator. Taylor's 2/5 scaling is a direct consequence of the interplay or balance or ratio of energy and density. In the same way, the final radius is the direct consequence of pairing energy and stress. Here, the time exponent is simply predicted to be 0. The last regime of the domain involving the energy is the initial regime, where the ejected mass is resisting. Let's reduce the size to make some room for the other regimes. The stress density regime depends only on the material properties of the ambient medium. It corresponds to the propagation of sound. The fifth regime we've seen gives the crossover size where the swept-up mass becomes greater than the ejected mass. So, 5 regimes, is that it? Not so fast. From a set of 4 elements, there are actually 6 pairs that can be formed. Here we have 1, 2, 3, 4, 5 regimes. We are missing the pair of mass and stress, which generates something we've never seen yet, a shrinking regime, where the size decreases over time. What is this mystery regime? We'll talk about it more when we discuss shrinking in the general series on mechanics. If you have ideas on what these regimes might be, let us know in the comments with the hashtag mass and stress. Could it be connected to implosion or collapse? For now, let's see at least where this regime would be with respect to the other 5. The regime dives down, crossing Taylor's regime around the time of the detachment of the shock. How this trend fits with the other 5 is much more clear if we prolong the other 5 regimes. This neat geometrical figure is a space-time projection of the explosion domain. It is what the interplay of energy, mass, density, and stress looks like when shown as the evolution of a size or sizes over time. This representation, as d versus t, is one out of many other possible kinematic projections. For instance, we could also be plotting the speed of the explosion versus the time, or the explosivity versus time. The domain is rotated and deformed by the different projections, but its topology remains the same. We'll see this in more detail in episode 8. For now, we remain in the size versus time perspective, because we have one obvious thing we need to talk about, the points of intersection of the domain. There are 2 kinds of points. 4 are at the intersections of 3 regimes, 3 lines, and 1 is at the intersection of just 2. We'll start with the black dots. They are the location of the 4 systems of objective units in the explosion domain. We've discussed 2 of those already. The first one we talked about in episode 4 is the Hopkinson-Kranz point. This point is at the crossroad of energy, density, and stress. The coordinates of this point are direct consequences of dimensional analysis. The trio E, rho, sigma implies them. Once we know the values of the mechanical parameters, we know where the space-time point is, where this event occurs. In the last episode, we talked about the early crossover given by energy, density, and mass. Here again, the coordinates of the events are direct consequences of dimensional analysis. Since our domain has 4 elements, there are actually 4 different trios we can build from it. For this domain, this leads to 4 systems of units. Note that this will not always be the case. For domains with different mechanical quantities, some trios may not lead to an intersection. We'll see a first example of this when we discuss the droplet domain, and we discussed this in the general series on mechanics. On top of the 2 systems we just saw, the 2 other black dots are associated with the trio of density, mass, and stress, or energy, mass, and stress. Just like the first 2 points, the coordinates of these additional events are direct consequences of dimensional analysis. There is no need to remember these formulas, because we know that we can recover them easily just from the dimensions of the mechanical quantities. Unsurprisingly, the top 2 lengths are identical, since these 2 points sit on the same horizontal line, and same for the bottom 2 points. These coordinates are spatial length and times, built solely from the combination of the mechanical quantities of the domain, 3 at a time. But why would we go through the trouble of computing all of this? If the only explosion we have is Trinity, then sure, we can pick one of the system of units and express size and time in these objective units. When we put an m between brackets for the y-axis and an s between brackets for the x-axis, what we are really saying is that for this plot, the size d and time t are divided by d unit meter and second. The systems of objective units provide alternative choices that are not based on human conventions, but on the mechanics of the explosion itself. We can use the E rho sigma units or the E rho m units or the E m sigma or rho m sigma units. The curve does not change, just the numbers on the bottom and left. For a single explosion, the choice of units doesn't really matter much. We know that systems of units start to make a lot more sense when we compare multiple explosions. Here are Trinity and a laser-induced explosion by Gruen and co-workers. These 2 explosions have completely different scales. When represented in conventional subjective units, it seems very unlikely that the physics of these 2 phenomena could be the same. Yet, we know that they belong to the same domain, the domain of explosions. For each explosion, we can draw the kinematic projection of the domain. We've seen Trinity. Here is the laser-induced explosion. By using objective units, we move the 2 domains so they overlap on one vertex. For instance, this is how the 2 explosions look when measured in objective units based on energy, density, and mass. Let's now do this on all explosions in our collection. We've seen this system of early units in the last episode. The 3 gray lines are the 3 regimes of this system where data overlap, at longer times that depart from one another based on their different values of stress sigma. Here is the full domain drawn for Trinity. Let's drop the shrinking 6 regime for now, we don't need it. The domain for the nuclear underwater explosion is slightly bigger. Much smaller is the domain for one of the conventional explosions. All the diamond-shaped domains are anchored on the same vertex, but they can be big or small. What sets the size of the domain for a particular explosion? Let's consider the other systems of units to see how things go. Here are the late units, based on energy, density, and stress. That is, the Hopkins and Krantz units of episode 4. Now, the late regimes overlap, but not the initial regimes. Here is the outline of the domain for Trinity, for the brown conventional explosion, and for the laser-induced explosion in yellow. Let's see how the data look when represented in one of our new systems, the one built from energy, mass, and stress. In this system of units, all initial regimes overlap, and the final blast radius are aligned. But the part of the explosion abiding to Taylor's regime do not overlap anymore. Here are the Taylor's regimes drawn for a few of the explosions on the plot. And now the same data in the last system of units. All regimes at sound speed overlap, while the shock eventually converges to. And the threshold sizes, while the swept up mass equals the ejected mass, are all aligned. But the Taylor regimes don't match. And the initial regimes don't match. It is like having a short blanket on a cold night. Pull it over your neck and your feet get cold. Cover your feet and your neck gets cold. There seems to be no other way than to arbitrarily choose the three regimes we want to overlap and let the others dangle. Well, there is actually a way to knit a blanket with the perfect size. We will do that in the next episode. Because first, we must introduce an important dimensionless quantity, which we can call the index of the domain. The four mechanical quantities of the domain combine to produce a single dimensionless number, independent of space and time, constant for each particular explosion. It is the only number that can be built from the interplay of energy, mass, density, and stress. We can drop the indices for the rest of this series since there will be no possible ambiguity. This index we're looking for must be some combination of energy, mass, density, and stress, with exponents gamma 1, 2, 3, and 4 to be determined. And we know how to do this. The left-hand side has no dimension, so the exponents of m, l, and t are all 0. For the energy term, we're just multiplying the exponents of the dimensions of energy by the unknown gamma 1. And we know where all of this is going. We're going to get three equations for the exponents of the mass, length, and time dimensions, 4 unknown, and 3 equations. So from any exponent we can express the other 3. For instance, the mass, density, and stress exponents can be expressed from the energy exponent. So any combination of the 4 mechanical quantities respecting this form is dimensionless for any value of gamma 1. So the index n, like any dimensionless number, is defined modulo an arbitrary power. We've seen this already with the Taylor set of number and the reduced Taylor set of number, which differ by a power of 5. The convention that we had followed to define the Taylor set of number was to seek the smallest non-fractional exponents, and we're going to do the same here, and define n1 as the case where the exponent gamma 1 is just equal to 1. This number, or powers of this number, show up everywhere once we start looking. For instance, let's go back to Trinity, represented in the Hopkinson-Krantz units. The coordinates of the origin are simple by construction, just 10 to the power 0, that is 1. What about the coordinates of the other remarkable spacetime points? We can turn back to the formulas for the 4 systems. Say we consider the Hopkinson-Krantz units, so the length and time in these units are just 1 and 1. To obtain the expression of the other length and times in these units, we can just divide all lengths and times by the units. The lengths simplify quite easily. The times also simplify to leave formulas expressed as powers of the index. So the coordinates of the 4 black dots can be expressed from powers of the index n. The length of the 2 bottom dots is n to the power minus 1/3. The time of the bottom right dot is n to the power minus 1/3. The time of the bottom left dot is n to the power minus 5/6. And the time of the top left dot is n to the power minus 1/2. So the 4 objective timescales are connected by powers of the index. The E rho sigma timescale is equal to n to the power 1/2 times the E m sigma time. and n to the power of 5/6 times the e rho m timescale. And the length scales are also connected by the index. Now, what about the remaining intersection, the white dot in the center? At this spacetime point, Taylor's regime intersects the shrinking mass stress regime. So if we call L and tau the coordinates of this point, we have a system of two equations with two unknown, which we can solve to get these ugly-looking formulas. In contrast to the four systems of units, these coordinates do not depend on trios of the mechanical quantities of the domain, but on the four quantities together. So these coordinates cannot be obtained by simple dimensional analysis. Yet, this point is obviously a direct consequence of drawing the six regimes of the domain. We will elaborate in future videos on the fundamental difference between spacetime points and the intersection of three regimes, the ones in black, and those at the intersection of only two regimes, in white. For now, it will be enough to remark that, just like the four other spacetime points, this one involves the index. After doing all this mess, we're now convinced that indeed, this index shows up everywhere. But what is this index? How can we understand it? In the first place, what is the value of the index for the various explosions in our collection? Let's first take Trinity and the laser-induced explosion from earlier. In each case, we can compute the value of the index from the values of the energy, density, mass, and stress. Since in each explosion these mechanical quantities are constant, then the explosion is characterized by a constant value of n. For Trinity, the bomb yield is 21 kiloton of TNT. This is around 8.4 10 to the power 13 joules. The ejected mass is around 9 tons, and the explosion occurs in the air, with density around 1.2 kg per meter cube and bulk modulus around 1.4 10 to the 5 Pascal. This leads to an index around 80,000. For the laser-induced explosion, the energy input is 200 joule, and in the last episode we estimated the ejected mass to be around 5 micrograms, and the explosion occurs in rarefied xenon, with density and pressure much smaller than in the air. This leads to an index around 2 millions. The value of the index summarizes the interplay of the four mechanical quantities in the domain. We can use it as a color code, with explosions with larger values of n appearing with a darker shade of red. We can apply the same color scheme for all the explosions in our collection. Note that for some of these datasets, no precise value of the ejected mass was provided, and it could not be inferred by measurements of the initial speed, so the index must be understood as a lower bound. And we will use hollow symbols to highlight these curves. When all datasets are plotted in seconds and meters, that is in standard or subjective units, the value of the index does not seem to reflect anything easy to pick up. But the relevance of the color scheme becomes quite obvious when the data are plotted in objective units. Here are the Hopkinson-Kranz units, that is the energy density stress units. Now the energy density mass units, the energy mass stress units, and the density mass stress units. In all of these plots, the closer the domain gets to the origin, the lighter the shade of red, and the closer log n gets to 0, that is, the closer n gets to 1. What is going on when n is equal to 1, and can n, the index, be smaller than 1? As we will see now, whether or not n is greater or smaller than 1 distinguishes detonations from deflagrations. Let's look at things in the Hopkinson-Kranz units. We've been dancing around something absolutely crucial to the understanding of explosions. All explosions we discussed so far were supersonic. Their index was greater than 1. They were detonations. This is actually quite obvious from this plot. The gray line on the right is the sound propagation regime. Since this regime is included in the system of units, this means that for all explosions on the plot, the gray line corresponds to a side growing at the speed of sound. All data points on the left of this line corresponds to explosion fronts moving faster than the speed of sound in the ambient medium. These explosions are then supersonic. They are detonations. On the other side, things move slower than the speed of sound. They are subsonic. And subsonic explosions are called deflagrations. All explosions in our collections are detonations. Before we turn to the absence of deflagrations, let's investigate further what the dichotomy sub-supersonic can tell us about the index. We've seen how the index can be understood as the link between the coordinates of the systems of units of the domain. For each system of units, the index also appears as a prefactor for the remaining three regimes outside the system. Take again the Hopkinson-Kranz units. The three regimes in gray are trivial by construction. They look mysterious in standard units, but once written in the energy density stress units, they are just simple equations. Now, what about the other three regimes that are not intersecting at the origin of the system? They are written here in standard units, not really appealing. But if written in the E-rho sigma units, they suddenly all involve the index. In particular, the initial regime involves the square root of n. If we focus on the initial regimes, which are the parallel lines with different shades of red, the further we go away from the sound regime, the higher the value of the square root of n, and so the higher the value of n, toward darker reds. In this system of units, the initial speed is just the square root of the index. The square root of the index can be rearranged so as to highlight the initial speed and the sound speed. So the square root of the index is the ratio between the initial speed and the sound speed. If the index is greater than 1, then the initial speed is greater than the sound speed, and the explosion is a detonation. Written in this way, the index is understood as the initial Mach number of the explosion. Some of the explosions on this plot have very high initial Mach numbers. For instance, the initial Mach number of the Trinity explosion is around 300. So the initial speed of the explosion is 300 times greater than the speed of sound. Now, what happens when the Mach number, that is the index, gets closer to 1? Most of the explosions we've been focusing on so far lack data for the initial regime. After doing a bit of digging, here are additional data from Tang and Baker concerning vapor cloud explosions. The Mach numbers are just slightly above 1, the highest being 5.2, so an index around 27. For these explosions, Taylor's regime has shrunken a lot, disappearing as the Mach number gets closer to 1. That is, when the initial speed becomes equal to the sound speed. What would happen if the initial speed was subsonic, for deflagrations? For these explosions, the log of n is negative, which means that n is between 0 and 1. Let's see what the explosion domain would predict. Take for instance this subsonic initial regime. Here, the index is said to be 0.1, which corresponds to an initial speed around 3 times slower than the sound speed. If the explosion happens in the air, this would give an ejection speed somewhere around 100 meters per second. At any time, the sound travels ahead of the ejecta. On a picture like this, the rough front of the ejecta moves at the ejection speed c0, behind the sound front. Both the sound and ejecta have the same origin, and this is quite clear in linear scale, where both curves meet where and when the explosion initiated. Since in log scale 0 is cut out, the two curves at constant speed appear parallel, although the two fronts remain similarly nested. The smaller the value of the index n, the further apart are the two fronts. In which conditions could a deflagration like this occur? Here, the comparison of the ejection and sound speed gives the index, which we set to be 0.01. Let's say that the explosion is happening in the air, with normal values of density and pressure, such that the sound speed is around 340 meters per second. Then, let's suppose that the ejected mass is around 10 kg. How much energy would be required such that the index is 10 to the minus 2? We can use the definition of n to get the energy, which would need to be around 10 kJ, which is equivalent to a few grams of conventional explosives, typically what you can find in large firecrackers. So how to make things work? We need an ejected mass of 10 kilograms, but the mass of explosive substance is around 1 gram. It's the active mass, and this mass is inside the firecracker. This active mass is where the explosion starts, but the whole thing ends up shredded. The casing of the firecracker increases the ejected mass. But to reach the 10 kilograms we want, we would need to embed this firecracker into a much larger mass of some sort, like in the watermelon, as in this benchmark experiment by the slow-mo guys. Here, the total mass of the watermelon seems to be ejected by the firecracker, but luckily at a reasonable speed. Let's rewind the clip to find a way to estimate the ejection speed. Here, see this chunk hitting Dan above his right eye? Let's follow it back to where it came from. For a rough estimation of the speed, we can divide the distance from the watermelon to Dan's face by the time it took for the debris to travel from one to the other. From the image, we can estimate the distance to be around a meter, and the film was taken at 2500 frames per second, so the time is around 20 milliseconds, which gives a speed around 50 meters per second. That's the overall speed, but was the debris moving uniformly for its entire trajectory? To check this, we can draw a line between the center of the watermelon and Dan's face. Then we can record the colors of the pixels along that line for the duration of the clip, producing a space-time plot like this. Here, the vertical direction is the space direction, going from the watermelon at the bottom to Dan's face at the top. The horizontal direction is time. The bright vertical line is the flash of light at the beginning of the explosion, the t equals 0. The chunk that we've been tracking was the first to fly out in that direction. Its trajectory, white on the green background, is quite clear. And indeed, it moved at a constant speed, since a straight line in this linear scale corresponds to uniform motion, here at a speed around 50 meters per second. So the Mach number of this explosion is around 0.1, which places the index well into the deflagration range. A firecracker in a watermelon seems to be an example of deflagration. Would you agree? You may rightfully have doubts, or at least questions. Something we're not really planning to discuss in this series, but which is quite obvious on this plot, is that the chunks coming from deeper inside the watermelon are ejected at lower speeds. Why is that? If we had access to the speed distribution within an explosion like Trinity, what would we see? Let us know what you think in the comments with the hashtag #VelocityProfile. But that's not on the program here, because we need to ask a different question. How far would the debris go if obstacles like Dan were not in the way? If we return to the plot in the Hopkinson-Kranz units, we expect deflagrations to initially follow the path of constant ejection speed. But what would happen later? In particular, does the ratio of energy and stress has an effect on deflagrations? Or is it solely relevant to detonations? Does anything special happen when the front of a deflagration reaches what we call the final blast radius for detonations? How are deflagrations influenced by the ambient pressure? We've not done our homework properly on this subject, so your suggestions are welcome in the comments with the hashtag Deflagration. Please tell us if you know papers tracking the front of deflagrations with different values of the Mach numbers smaller than 1. We would love to add blue curves on this plot. Our preliminary search suggests that In many cases of deflagrations, what eventually limit the propagation of the front comes from additional mechanical quantities beyond the explosion domain, like the weight per unit volume, for instance, which tends to pull the debris down. But this would require to study the effects of not just 4 mechanical quantities, but 5, something we're not yet ready to do.